So I mentioned in my last video that I have a probability exam on Thursday, and I wanted to show you some of my notes that I use to study. So these are throwaway notes. I'll write this down, and eventually I'll throw it away when I'm done studying them. It's just I like having something to write on. It is kind of a waste of paper, but I need to write on something. But I try and use all of the space more or less that I can. And I do write big, which is another issue, but whatever. So what I'll do is I'll look at his syllabus that he gives, and I'll go through each topic that's on the list and try and make some sense of it, write down what he has in the notes. So we have a probability space and a random variable defined on omega. You have finite first moment. We have a partition. We collect all sets of measures 0 and call that C0, and then everything else has positive measure. The partition, that is. We then define the expectation of x given Cn to be 1 over the probability of Cn times the integral of x over Cn for all n bigger than or equal to 1. It's not defined for 0, but I think we just define it to be 0 at C0 because it only happens on a set of measures 0. So no one really cares. This can also be rewritten as the integral of t times the differential of the distribution function fxn, or fxcn. And that definition is given here, which that just follows from the elementary statistics definition of probability. And then using those expectations, we can define the following random variable. The expectation of x, given that we have the sigma algebra generated by the partition, to be this following set here. Or not set, but this function here, where it takes those constant values over C0, C1, yeah, so on and so forth. So that page was just definitions, and then these next couple pages talk about different properties. And rather than go through all of this stuff here, because I recorded this video previously and I didn't really like how it turned out, so I'm going to skip ahead to the page that has all of the properties on them, which is given here. If we have a family of random variables, x and y are integrable random variables on the same space, f and g are sigma fields contained in the big sigma field E, then we have the following 9 properties. So what's the first one say? If we take the expectation of x given g given f, then this is the same as if you replaced f with g and g with f, and then that reduces to the case of we have the expectation of x given f, provided that f is inside of g. In his notes, he calls this smaller sigma field wins. Property 2 says that if you have the measure of x equals c equals 1, then we know that the expectation of x given g is equal to c. I think that comes from the fact that the c pops out and then you just get the measure of the space equaling 1, so you have c times 1. Again, don't quote me on that. It's just I'm trying to go from memory here. 3 is the linearity property. So a and b come out, x over g, y over g. 4 is the monotonicity property. X less than or equal to y, expectation of x less than expectation of y. 4 is the triangle, or excuse me, not 4, but 5 is the triangle inequality. 6 is monotone convergence. 7 is dominated convergence theorem, I believe. Yes, that is the case. What does 8 say? Y is g measurable, expectation of xy is finite. Oh, the y comes out. Okay, so you have a random variable where y comes out. And y need not be integrable, but x times y is integrable. All right, fair enough. 9, I don't really know what to make of 9. 9's kind of strange. You have a probability space, x is a random variable, finite first moment. T is the smallest sigma algebra. G is another sigma algebra, then you know that the expectation of x over t is equal to the expectation of x over g, or given g. I say over g, but I should say given g. And that is equal to the expectation of x. Whatever. Conditional Jensens. Okay, so the other day, I mentioned in the video about mentioning conditional Jensen's inequality to the instructor, so he added this when he forgot it. And what it essentially says is that you can create new random variables from old. If you have x as a convex function on I, and you have x being a random variable that takes values in I, my interval, and you assume that x and fx are integrable random variables, then for any sigma field G contained in E, you have this case here, where the expectation of fx given G is bigger than or equal to f of the expectation of x given G. So Jensen's inequality is about convex functions, and a convex function essentially says that if you have this curve given by f, then if you pick any 2 points on the curve and connect them with a line segment, the line segment always lives above the curve. It never dips below. And that has to be true for any 2 points that you pick. Or at least that's a very rough definition of convex function. In this case, it's kind of hard to see, but we can make sense of it. All right, so there's a bunch of other stuff in chapter 6, but I decided to skip it because I don't want to be here all day. And then we have chapter 7, which is about martingales. And we'll look at the very first page here. If you have a probability space and a family of random variables over omega, and you have a sequence of nested sigma algebras, G1, G2, G3, so on and so forth, and you have the following three properties being satisfied, where xn is gn measurable, you have finite first moments, and probably the important one, well, they're all important, but you know what I mean. Number 3 is the case where we consider, it's the thing that gives us the martingale is what I'm trying to say. The expectation of xn plus 1 given gn is equal to xn for every n. This is called a martingale if these 3 are satisfied. If instead you have less than or equal to, then it's called a super martingale. If you have greater than or equal to, then this family is called a sub-martingale. And then using Jensen's inequality, we can create new martingales from olds. So given a sub-martingale, and you have a non-decreasing convex function R, and the expectation of fxn is finite, then this new family of random variables is a sub-martingale. Similarly, we can get other martingales using xn plus and max of xn over a for fixed a. Those also give us sub-martingales. And if this is a super martingale, I think if you consider negative f, then you also get another super martingale. Although I have to make sure, I have to check to make sure that's true. Okay, Doob's decomposition. I'm not interested in Doob's decomposition. I mean, it is kind of interesting, but I don't really feel like talking about it right now. But he's only requiring us to know the proof of one theorem from the notes, and that's Doob's maximal inequality. And it's a pretty short proof, and it's familiar to us if we are, from the previous semester, there was another proof that we had to know that had a trick in it, and it's the same trick that shows up here. So I think that's probably why he wants us to know it. So what does Doob's maximal inequality say? It says that given a submartingale, then for any c in the real numbers, which I'm looking at this now, I feel like it has to be This has to be positive real numbers in order to make sense. Otherwise, if it's negative, it doesn't make sense. So, but whatever, we'll just keep going. What it says is that the probability of this set, where you have the maximum of xk bigger than or equal to c, has to be less than or equal to 1 over c times the integral of xn over b, which is less than or equal to the expectation of xn, where b is the set that we're measuring here. So how do you prove it? The proof is kind of slick, and it's not too long. You can see I've done it here in 4 lines. The way that it's proven is that you create a partition of omega, and the way you partition it is that you define A1 to be x1 bigger than or equal to c, and then you define A2 to be the set of all omega such that x2 is less than c, but x2 is greater than or equal to c. Or excuse me, x1 is less than c, x2 bigger than or equal to c, and then you just keep going up and up and up and up and up. So for an, you have xk less than c for k between 1 and n, and at the nth random variable, you have greater than or equal to c. So you have this partition. And then you just set up the inequality. So we have the integral of xn over b is equal to the sum of the integrals of xn over ak, which makes sense because ak is a partition of b. And then we can rewrite expectation of xn over gk in place of xn. And the reason that we can do that is because we have a sub-Martingale, I think. No, wait a minute, they're equal to one another. They're equal to one another by the property of by this conditional expectation. All I'm saying is that these two are equal over ak. And then you use the sub-Martingale property here. So I can replace this expectation, or this random variable, with this random variable over xk. Okay, so then what do we say? So I know that over ak, xk is bounded below by c. That's by definition. So I replace this with c. C is a constant, so I can pull it out. And then I end up with this guy. And then this integral is just equal to the measure of ak. And since it's a partition and I sum them all together, I'll get the probability of their union, which is what I have here. Although that's less than or equal to. Why isn't it just equal to? Because they can't overlap, right? I don't think it matters in the end, to be honest, because we still get our inequality. But I just don't know why I chose to write in it less than equal to rather than equal to there. Anyway, I'll see it later. But the probability of the union is the probability of B, because that's the definition of B. It's the union of all those. It's a partition. So if you union them, you'll get B. So you have C times probability of B. Divide by C. I mean, I can't even... Now, this is actually kind of stupid up here, because I can't have 0, otherwise I'll have division by 0. So this has to be non-negative reals in order to make sense. So we got to make that distinction here. So if I divide off the c, then I'll end up with my inequality here and everything's done. So it's a very short proof, and I don't think I'll struggle to recite it on the test come Thursday. We have Doob's upcrossing inequality. I don't really like that inequality, to be honest with you. I don't really understand it too well. We have the sub-Martingale convergence theorem, where we have a sub-Martingale, and we know that the supremum of x plus n is equal to k for all infinity, so they're all bounded. Then there exists a random variable, finite first moment, such that xn converges to x almost surely. Okay. And then uniform integrability shows up. This is just more definitions, equivalent definitions of uniform integrability. And I know that somewhere in here that Doob's martingale is the only uniformly integrable martingale. It's in here somewhere. Stopping times. I don't even know. Who cares about Doob anyway? We'll finish up this video talking about stopping times, and I might show you some of my problems that I decided to write up. But anyway, so what's a stopping time say? A stopping time is a random variable that's integer valued. So t is a stopping time, so it's defined on the space S. It takes on extended positive integers. And it is a stopping time provided that the set of all omega such that t omega is equal to n is a gn measurable set for every n. All right, so what can we say about stopping time? So I just wrote a couple. I'm not done actually taking these notes here. I'm just reviewing what I have written. So the following are equivalent. T is a stopping time if and only if t less than or equal to n is a gn measurable set, if and only if t bigger than n is a gn measurable set. That comes from the fact that these two are complements of one another. And it's not too hard to show this one either, because remember, they're sigma algebras, these GNs. We can make new stopping times, so the sum of two stopping times is a stopping time, minimum is a stopping time, minimum Tn gives me a sequence of stopping times, so many different stopping times. And then there's also the stopping time theorems, or the OSTs, what are they called? Optional sampling theorems. There's like 3 of them. And I think I was so lazy I didn't even write them down. So I need to write those down before Thursday and understand them. What I really need to do is just go through the examples. But I'll do that off camera. I don't want to bore you guys to death. Okay, so what do I have here? So this is something completely different. On Monday and Wednesday, I meet my analysis instructor, and we discuss various analysis-related concepts. And he's asked us to, if we want to start preparing for qualifying exams, which we all definitely do, he's told us that we can bring some stuff together and we can start working on those together as a group, which I think every single person wants to do. And one thing that I do is I work problems, and I try and find stuff on the internet to practice with, because he encourages us to do that. But I also try to write my own problems, and unfortunately I'm not very good at it. What I try to do is I look at problems I have done and then tweak them a little bit. So I start at the very end and then work backward to figure out what assumptions I need to give my instructor, see if he can solve it, and see if I've made any mistakes. And I know I've made mistakes, but is there any benefit to doing it this way? I think there's something to it. It's just me trying to get into the head of one of my instructors to see if I can actually prepare one of these things. So in case if you're interested, oh, by the way, if you're wondering what happened up here, I wrote my name on it and I decided to peel it off, because if I wanted to show it to you, then obviously I'd have to rip it off. I understand that my analytic number theory video had my course number in it, so I also don't think, I think that if someone was determined to figure out exactly who I am and what my name is, they could figure it out. You just have to dig a little bit, but it's not like, and ultimately I don't really care that much. It's just that enough people watch these videos to the point where if I just have one person figure out what my email address is and then, start emailing me constantly, that's the only thing I'm really interested in not happening. I just don't want to get a bunch of emails from one guy wanting me to do stuff. But in general, I don't want to discourage it either. Whatever, let's just do these problems. So what does the statement say? Fn is defined on the unit interval, bounded below by 1, Borel measurable. You have the following assumptions on the two integrals, where an is a sequence that asymptotically grows like the square root of n. So I wrote that comment down here in case it wasn't obvious what I meant by this statement up here. We want to prove that Fn cubed cannot converge to 0 almost everywhere. I think this statement makes sense. I had a problem that I looked at, and I don't think I've done anything wrong, but there may be something I'm not seeing. And the same is true for all of these problems. But if you want to take a stab at any of these problems, go right ahead. They're not super... I admit they're kind of contrived, but I'm trying to write problems the way that I might see on a qualifying exam someday. But whatever, we'll do number 2. So M is a Lebesgue measure on R. E is a Borel set. Negative E is equal to the set of all negative x and e. Fix a positive constant C. We want to construct a non-trivial locally finite sign measure on all of R, such that for any Borel set E, the mu measure of E is bounded above by C in absolute value. And for any F that has the property that it is the union of E and E negative E, we know that the mu measure of F is equal to 0. I also make the assumption that the mu measure of x plus is equal to the mu measure of x minus, where x plus is the set of all sets of... Wait a minute, what am I trying to say? It's the subset of R such that the mu measure of subsets of x plus are positive, and x minus for sets of negative measure is what I'm trying to say. And the reason this problem is kind of wordy and really long and contrived is because I was trying to get the person answering number 2 to come up with a function similar to what I had in mind, or a sign measure that I had in mind. And I wasn't very good at communicating what I wanted the function to look like. I had something very specific in mind, and I wasn't doing a very good job of explaining it. So if you can solve if you can get number 2 with what I had in mind, then I've succeeded. But if it's impossible to answer, then I failed, and I need to go back and redefine the problem. But I don't think anything here is inappropriate. Everything that I've asked for the student to do taking this problem, I think they can. It's just getting your bearings is the only thing that's a problem. So what does number 3 say? We have a partition on R. The measure of each set is positive and finite. Fn is a sequence of functions such that Fn is only positive on En and 0 everywhere else. If Fn converges to F almost everywhere, then prove that prove that the sequence of integrals converges to this integral. Number 3 may have an issue, and it's because Fn may not be properly defined enough for me to make this conclusion. So 3 is the only one I'm kind of worried about. But if you want to try it, or if you have a comment about how to fix it, I'll read it and see if I can change it in some way. But I definitely had something in mind when I wrote it. And then number 4, I actually don't know how to solve off the top of my head. It was just I was thinking about sequences, and I wanted to see if I could make a problem where I show some series converges. So let the sequence Fn be the Fibonacci sequence, and we want to find all positive alpha such that the following sum converges, where I look at reciprocals of Fibonacci numbers. And the reason I picked this problem, or came up with this problem, is because I was thinking about how the reciprocal of positive integers diverges, but the reciprocal of squares converges. And the same thing with reciprocals of powers of 2 converge. So those are some basic examples that you read on any Wikipedia page. But I was thinking about like reciprocals of primes. If you add up the reciprocals of primes, that diverges. And I was thinking of other famous sequences, and the Fibonacci sequence came to mind. And it wasn't immediately obvious to me if it converges or diverges. And I didn't spend too much time writing number 4 because I got kind of tired after writing 1, 2, and 3. So I just threw it on here. I'm curious to see if my instructor, what he'll do for number 4, if he's, willing to take a stab at any of these problems. So this video is kind of long, and if you're interested in trying these yourself, then you can click off the video now. Otherwise, I'll give you hints as to what I had in mind for each of these problems to see if that, will steer you in the right direction. So problem number 1, I had the Cauchy-Schwarz inequality in mind for this guy. Now that I'm thinking about this, AN I might need some sort of bound on AN in order to make it make sense. Actually, you know what? I think it might be fine. Never mind. But Cauchy-Schwarz is the trick I had in mind when I wrote number 1. For number 2, I had the Radon-Nikodym theorem in mind. It's a sign measure, but you can still define a measure as the integral of some function times dx, or dm, where m is your Lebesgue measure. So the way I think about it is think about even and odd functions and then multiplied by some really fast decaying function. So really, number 2 is all about defining your measure, your sign measure, as some function times the differential of the Lebesgue measure. Number 3, the hint is you want to use Lebesgue's dominated convergence theorem, so you need to figure out what kind of integrable majorant you have on this function inside here. And I think because Fn is 0 on the complement of En, everything's fine. But there may be an issue. I just don't see it just yet. And for number 4, again, I told you I don't really know how to solve it immediately, so I would just consider looking it up on the internet. I'm sure it's out there somewhere, in which case I hope the answer is interesting, because the Fibonacci sequence is recursive, and I'm not entirely sure how to do it for a recursive sequence, at least right now. I haven't really studied recursive sequences too much, which is one of my weak spots. But anyway, so that's what I've been working on recently. Thank you for watching the video, and consider subscribing if you haven't. Every little bit helps. Thank you.